Hello, everyone. We're going to let everybody in and say hello, and we'll start in a few minutes. So, again, I'm Ellie Burns. I'm the host and marketing director here at Rise, and I'll let the other two folks just kind of say hello. And I'm going to chat some things into the chat so you guys can see some instructions for how to interact with us. So, I'll let you guys go ahead.
Go ahead, Mike. No, please.
Hi, everyone. I'm Mike Fingeroff. I already see some familiar names on the attendees list, and welcome to this webinar.
And likewise, hello, old friends and new friends. I'm Alan. Happy that you could join us today.
Sorry about that. I've got a small screen that I'm working with today. So again, thank you guys for coming. Today's presentation. This is the fourth one that we've done. It's called Yes, HLS Can Be a Game Changer for Control Logic and Learn How to Make It Work for You. So I'll tell you a little bit more as we go through this about why we decided to do this webinar, but I'm really excited about this content because this is something new that we've been doing. So what we're going to do is first, I'm going to give about a 10-minute introduction, just really, really high level. I will point you to some other resources. If I'm saying something that you want more information, either ask us a question or I'll point you to some other webinars where we've talked about some of these things. But I just like to kind of level set before we then turn it over to Mike to give a big deep dive into the technical content that we've got prepared for today. So really quick, if you don't already know, I see several folks who have come to a couple webinars before, but if you're new to this, we're Rise Design Automation, and really our mission here and our focus is to deliver implementable, verifiable, high-quality RTL in a method that's practical and exists today and dramatically improves the productivity of generating that high-level RTL. We were founded in late 2022, so we're excited to be a new EDA startup, and we officially launched this last year, 10 employees in the US, and really excited to be able to be talking to you today. So at the high level, what we're doing is we combine raising the abstraction of design and verification plus synthesis plus intelligence, and looking at that, raising the abstraction in C++ or System C or SystemVerilog. And today we're going to focus on SystemVerilog because we haven't done seminars where we really focused on the SystemVerilog part, but you can do a lot of these things in System C and C++, and we support all three of those languages for a raised abstraction. The nice thing about SystemVerilog, it's more familiar for RTL folks. You get to preserve more of your DV ecosystem. And then you can do a lot of things that Mike is going to be talking about today. He'll give you a demonstration of how exactly to do that. Next over here, then we have a full high-level tool chain. So synthesis, verification, debug analysis, exploration, and AI to go with that for both design, verification, generating help. So complete AI, generative AI solution to go with the high-level chain. And then again, we want to make sure that we're seeing right now a lot of different ways to help design, help verification with AI, but our AI has really been focusing on combining the human intelligence with the high-level tool chain and making sure that the RTL you have is practical, but also very verifiable, high Q of R, and readable. So again, that's really what we've been differentiating with. It's a very unique solution for hardware design. In case you're not familiar with what we do, I'll start here. It's really taking that high-level design, whether it's untimed or loosely timed, using our tool chain and turning it into high-quality RTL. So in a nutshell, that is what we're doing. We are taking a higher level of abstraction and turning it into high-quality, high Q of our RTL, which Mike will show you a little bit more. And with that, we have a set of generative AI advisors and agents to answer technical questions. And we've done a couple of really great webinars on this already. So if you want more detail on that, you can enhance the code quality. And it really is focusing on having that high-level design expert, somebody like Mike, sitting side by side with you to help guide you, help generate code, help answer questions on the tool. Very fast, high and mid-level synthesis will we'll talk a little bit more about that as we go into what is the high level versus the mid level. How do you add more time, which is what we'll focus on today. High level verification, again, it's much faster and easier to verify at this level of abstraction. And most of the customers do 95% of their verification at the high level. You just have a few more things at RTL to check off. So it gives you tremendous productivity and verification. And then we have a full set of debug, analysis, and exploration tools. So that's kind of in a short nutshell. The other thing that we're finding is that because we can support SystemVerilog and C++ and System C, and we can interact and we can mix and match those, it enables a much greater collaboration across software teams, across architects, across RTL, because now you can have different blocks and at different levels of abstraction, and you can combine those. So it makes it much easier to both come up the learning curve from the RTL side and to meet in the middle from the algorithmic side. And again, with the SV support, you get to keep your existing SystemVerilog ecosystem. So you don't need to change what is your verification environment that you trust and know about. For this slide, it's mostly a verification slide, but I want to do a quick introduction of kind of some concepts. The first one is to look at kind of, the more you kind of take out events from simulation, the faster things get. So the very fastest simulation is pure untimed C++. And then we also support untimed SystemVerilog. That is threaded C++. That's threaded. So you get a few more features, you get the threading, but still untimed. And so it goes a little bit faster. Today, we'll spend most of our time here in loosely timed, basically SystemVerilog or System C. And that gives you the ability to do much more control, adds more concepts of time. And it slows down the simulation a little bit, but you still have, 30x to 100x speed of RTL. And then finally at the bottom, you have RTL. So again, look at these different levels of abstraction, both for verification, and makes it much easier to design. And Mike will talk a lot more about that today. So I kind of introduced a little bit about the AI solutions, intros to HLS, about what we do with our debug tools, with the infrastructure. All of these are available in on-demand webinars that we've done already. Here's the link, and I'll send this out again today with Rise LNL. It's just one password to get to everything. We would just want to make sure that that you can look at any of the content that we have. So again, that's all there for you to look at besides the webinar that we have today. Okay, so last slide for me, and then I'll turn it over to Mike, is I just want to make sure if you guys are not familiar with high-level design, raising the abstraction is proven. This isn't brand new technology. We're new to it, but high-level design has been proven over the years to dramatically improve the productivity. In AI and video, we have multiple customer things where you get 10x productivity, cut your design times in half, and all of this has been proven on production level designs. But I think we're here today to really talk about whether the hardware block that you're thinking about doing, the design that you have, whether that's a good fit, because that's one of the biggest questions that we hear. Like, is the design that I'm doing, is that a good fit for high-level design, high-level synthesis? You hear a lot of times that datapath, data flow is very good, but what about control? Right? Can I get the quality of RTL? Right? You have to get the same quality as you can with hand-coded RTL. Can I get that functionality and detail, especially for control logic? And again, I think there's been a myth out there that HLS doesn't do control well, and it's really hard. So what we wanted to do today is give you technical methods and have Mike talk directly to that on busting that myth today. So I'm going to turn that now over to Mike to step through exactly how to do that.
Okay, thank you, Ellie. So I'm going to talk about what control looks like in HLS, and this is not going to be digging into how to do HLS, but I just wanted to put this slide up here to say, well, what does HLS do? And I think everyone that I can see in kind of the list of participants, a lot of them already know this, but high-level synthesis converts untimed or loosely timed SystemVerilog C++ or System C into synthesizable RTL. Pipelining, so basically inserting registers to meet clock frequency constraints based on timing is done automatically. That's a big deal because you don't have to worry about timing closure. Data flow control is built in, so we'll look at these interfaces because now we're going to start to talk about what does that mean in terms of control. You get to explore parallelism and pipelining, doing things such as unrolling loops to execute them in parallel and things like that. We're not really going to focus on those kind of knobs that we could turn into HLS. And along with that, you designing using memories, which is something that you can think of that is involving control, is automatic because you can turn arrays into memories and the address data and control signals are added automatically, or they don't really get into memory synthesis for this presentation. So why does high-level synthesis simplify control design? So the first thing is that you use transaction level I/O when you code for HLS, and this abstracts away low-level protocol logic. So instead of having to think about how am I going to get data into and out of the block, how do I implement flow control? The transaction level I/O have built-in ready valid signals that allow you to basically automatically take care of data flow control, and that's going to start and stop the pipeline depending on the availability of the I/O. And the FSMs that are involved in basically coordinating all the different I/O are generated automatically, and they're really implicit in the design description. For all the languages, we have these transaction level I/O, whether it's SVAC channel for SystemVerilog, which is what we're going to look at today, matchlib for System C, and AC channel for C++. And with this modeling style and really with the synthesizable hardware, control and data move together, which makes it very easy to build designs and really scale up. Coding control in SystemVerilog C++ and System C is very natural, and it really looks very much like what you would do in RTL. But really, you're doing it in terms of using conditional logic within your design, whether it's if-else type conditions, switch statements, and things like that. And by basically coding in a high-level language, it's going to enable you to build designs faster, prototype faster, and the code's very clean. Along with this, then, and this is where it starts to be somewhat different from designing an RTL, is that loops are synthesizable in high-level synthesis. So in RTL, a loop is going to be synthesized as a parallel data structure, and that's not the case with high-level synthesis. Unless otherwise specified or depending on the use case, a loop is going to be left rolled, which is going to be synthesized basically as an implicit FSM that controls a scheduled data path. So a scheduled data path is essentially, a data path that has been timed by the synthesis engine. The loop carry dependencies are going to create control logic sequencing automatically. And what that really means is when you write a loop, you're going to have some loop counters that's going to tell the loop when to increment and when to exit. And all of that is going to be automatically synthesized into underlying implicit FSM. And the beauty here, it's an advantage, and we'll see it can also be a limitation, is that this eliminates the need for manually coding state machines in many cases for basic control flows, and it's quite powerful, but not necessarily always what we want. Some of the challenges when designing control and high-level synthesis, kind of related to what I just talked about, is that control logic ends up being somewhat less deterministic than data path logic. I/O can be reordered based on the analysis of the synthesis tool. The control paths are going to be, optimized based on the inferred behavior. FSMs may be implicit, and what that means is that, even though it's fundamentally creating an FSM under the hood, it's really not, it doesn't look like an FSM in the classic sense, where you have a switch statement with explicit FSM states. And so that may be harder to understand and debug. And then also, because we're doing high-level synthesis, latency latency can be added by the tool, and that's somewhat different than what the code implies when you're just looking at it visually. Another issue is that timing behavior is not always visible in the high-level code. Because we're kind of the default, the most commonly used coding style is using this transaction level IO, where it will block if data is not available. That you can't really understand, from looking at the source or simulating with blocking IO, what some of the challenges might be when you actually generate the RTL. And as we'll see, it's often not sufficient for implementing control type designs. Using those constraints I talked about, pipelining and loop unrolling can change the latency of the RTL. And really, you need to model what you're trying to do if you want to be able to simulate at a high level and kind of expose some of these potential control bugs. And what this really means is multi-threaded simulation. And I'm going to be focusing on multi-threaded SystemVerilog. The same is true for C++ or for System C. And one of the limitations currently, I'd say, in the industry with C++ is it's not really truly multi-threaded. This is something that we've looked at, but as we'll see, when trying to do control type designs, it's hard to actually simulate at the high level what the true behavior is. Often precision control requires deliberately modeling at a more RTL style, and we'll see what this looks like between the different coding styles. And so, what you often do with high-level synthesis is you kind of do what any, RTL designer would do, is you partition and you think about separating, things where you need explicit control from the data path for clarity. Part of this, as we'll see also, use of non-blocking IO is essential. So blocking IO, we'll look at some examples. It's very simple, but it really is limited in how far you can go. And then ultimately, with the use of non-blocking IO, it allows you to simulate and then synthesize and end up with the same or very similar cycle accurate behavior. So what do we mean by control versus data path? So data path performs the computations and control drives the behavior. So data path means, ALUs, multipliers, multiply add trees, shifters. It's the math in your algorithm that you're implementing. And the control logic is doing the selection of that computation. It's managing data flow control, and it's initiating operations within the source. So when you end up with a scheduled pipeline, the data path is moving data or values through the pipeline while control is essentially advancing the state. Control logic is responsible for sequencing, operations and managing the overall timing or behavior of the design. It determines when inputs are going to be read and when outputs are going to be written. It coordinates, conditional branching and state transitions within the data path, and then also as part of that conditional branching enables resource sharing and decision making between the different processes in your design. So again, sometimes separating these concerns helps with, not only clarity and understanding what the different portions of the design are, but also with synthesis and being able to do debug. As we'll see, there are reasons why you might want to combine control and data path, and other reasons why you might want to separate them. Okay. So let's talk about I/O. So with high-level synthesis, we have essentially two types of I/O, excluding wires. So wires are supported on high-level synthesis, but that's typically really used for things like configuration status register interfaces because there's no synchronization. So we have both blocking and non-blocking I/O in high-level synthesis. Blocking I/O simplifies the code, but it's hiding the control flow. So you have operations for these transaction level interfaces where you're just calling a function, either a read or a write or a push or a pop, depending on the language that you're using. And if you don't need complex control within the design, it's a simple feed forward data path. This is ideal because it's very easy to get the design right. You're not going to do a lot of debug either at the high level or in RTL. But This stalling mechanism is implicit in the design description, and it makes it harder to understand what's going on when things are start to not behave as expected. Non-blocking I/O exposes the control decisions at the high level, and so there are functions for the transaction level I/O, such as MB read and MB write, or pop NB and push MB if you're using System C. And this allows you to test the readiness of the I/O and determine if data is not available, let's do something else. And so this is ideal when you're really trying to do more RTL-ish type things. But what we're going to see is that it also still allows you to code at a pretty abstract level, much higher than compared to RTL. And so ultimately, it's up to the designer to decide based on your needs what type of what type of I/O to use depending on the design. So let's look at a couple simple examples. So here's an example of blocking I/O, and I'm not going to go into all the nitty-gritty details of the different types of methods that are available, but really fundamentally, most of the blocking I/O have two methods. They've got a read method and a write method. And so if you look at this design here, so this is synthesizable SystemVerilog that's going to be an input to the RISE high-level synthesis tool. I have some abstract SVAC channel interfaces where I get to define the data type and then I name the channel. And the data ready valid signals, when this is synthesized, are going to be added automatically by the synthesis tool. And that flow control is going to be plugged into the pipeline control to start and stop the design. In terms of coding, it's quite simple and it's very clean. I basically do a data in, which is in this case, my input channel name, and a dot read, and it returns the data when it's available. Same thing with the output channel. I do a data out dot write, and this is going to attempt to write the data to the output channel, assuming that data can be received. And so this in itself is a very powerful control feature of high-level synthesis, because if you look at the simulation now, when I synthesize and simulate this design, the design comes out of reset, and then the input channel data in asserts its ready signal and drives it high. Just in case you're wondering, you'll see things happening on negative edge clock cycles, and that's just the simulation transactor. And the little glitches are also an effect of the simulation transactor, so nothing to worry about. But so ready goes high, which is the hardware saying, hey, give me some input data. And then when it samples the valid high, which is in this case coming from the test bench, the transaction completes. And so this data ready valid handshake is essentially allowing me to send data, in this case, once per clock cycle. So you can see ready and valid are high once per clock cycle. And then this is where things get interesting, is that the test bench stops sending data. And at this point, then the pipeline will automatically flush because we have a bunch of data that's in progress in the pipeline. And then once the pipeline finishes flushing, the output is going to stall. And then at some point, data becomes available again. And at some point later, once the pipeline ramps up, it'll start producing data again. So extremely powerful feature, because we've added back pressure into this design, and you as a designer don't need to worry about writing FSMs to manage the data ready valid of all these different IOs. It's all done implicitly as part of the synthesis process. So what's the problem with blocking IO? Really, there's a big limitation. So blocking IO always stalls the pipeline. So if one IO blocks, all IO is going to block. And this means that you can't check to see if data is available, do something else. It means that if you have blocking IO, and in this very simple example now, I've added see if I can add a laser pointer in here. I now have two channels, two input channels, two output channels, and I'm just reading the data and I'm forwarding the data on. But the problem now is if say the data in 0 channel blocks, that means I can't read data in 1 and I can't output data in 1. So the whole pipeline stalls, and so there's nothing else to be done. So you can see that despite being a very powerful coding style and synthesis mechanism, blocking I/O has some real limitations. It's great for feed-forward data paths where data is coming or not available, but it really limits you in the code of what you can code in terms of control. So this is where you use non-blocking I/O. So non-blocking I/O, it gives us a lot more power. It allows us to kind of code closer to RTL, but we're still able to do things at a transaction level. And that's much more powerful. It's much more flexible than coding at the RTL level. The other thing, and I don't get into it as much here, but it's really a reality, is that in order to simulate this and verify it, you really need to be able to do multi-threaded simulation, because if you're not able to simulate multi-threaded, you can miss scenarios of something like if you're doing arbitration. We'll look at an example in a second here. So I've taken that same design from before where I have 2 input channels and 2 output channels, and now I'm using the MB read methods. And what this means then is that MB read will return a valid bit indicating when data is available. So it's actually checking the incoming valid signal for the incoming channel, and it's returning that to say, yes, data is available. And if it returns true, then it's actually going to return as an argument to that MB read function, the data. And then within my code, I can have conditional checks based on that valid or a data availability, and I can do something. So in this case now, I'm checking to see, okay, is the data in 0, 1 channel, did it read and is data available? And if it did, then take that data and write the output. And I do the same check for the data in 1 channel and write that output. And what you can see now from the simulation is that in the simulation, only data in 0 is available. Data in 1 is just not being driven. There's no data in 1 availability. And so now what you'll see, though, is that even though I don't have any data on data in 1, the data in 0 data is going through the pipeline, is then being written to the output. And it also is showing the same stalling mechanism here where data in 0 is not available. So this is in effect allowing me to make decisions based on I/O availability. So that's a pretty simple example, and this is where it starts to get more interesting. So as I mentioned before, coding style is still high level compared to RTL. You have to manually manage the flags. So there's more detail that needs to go into the code, but if it's more complex control, then you're going to need more complexity in your code, but it's still much higher level over RTL. The I/O is still transaction level. So ultimately, the management of the ready valid flags is still being added by the synthesis tool. But this really opens up the possibility for doing many more design styles or types, such as arbiters, cache controllers, DMAs, things like that. And it also allows me to model at a cycle accurate level. The thing that needs to be combined with that is by modeling this way, if I really want to ensure cycle accuracy between the high level model and the synthesized RTL, I also need to apply some synthesis constraints. And so we have the ability to tell the synthesis tool to force this design to be a single stage pipeline with an II of 1, which is saying I want basically a throughput of 1 on the input and output I/O. And so now, if you look at this slightly more complex example, what I'm doing here is I've created an arbiter that's essentially arbitrating between 2 input requests, and it's doing resource sharing. In this case, the resource is just a multiplier, and I've kind of built the data path into this control design, which you can do. We could also just do pure control and maybe forward the control to a separate data path, but this kind of shows the general idea. So now I have some state flags and state variables for storing the data. I've got a state that's, in this case, this arbiter is doing round robin arbitration, where each time it evaluates, it'll flip the priority. And then the flags are used to basically indicate when a data is available in I/O. It's going to store that, and it's going to wait until that request has been serviced. So in this example now, I check to see if the flags are not set, which means there's no data that's been read. So if the flag's not set, it does a non-blocking read in this case. It sets the flag, which means now until this request is going to be serviced, it's going to hold the data and it's going to hold the flag value. And it means it won't reread the IO, so it's not going to overwrite anything. And then I've got my my arbitration logic basically where it's going to check, did the flag get set and do I have priority? So again, this is round robin priority. Or if the flag got set and I don't have access, but the other flag is not set, then go ahead and now you're getting access to this resource. And it goes ahead and it does the multiplication. It clears the flag because it's now serviced the request and it writes the data to the output. So again, pretty simple, more detailed than just regular data flow control for feed forward data paths, but very powerful. Okay, let me just do a quick time check here. So when you're modeling, depending on how you write the code, you can end up with an implicit FSM. And an implicit FSM means you haven't explicitly coded an FSM, but based on the way you've written the code, you are going to get essentially an FSM that's going to control your design. So control is essentially inferred from the code structure. And this typically happens when you have sequential statements that are implying state transitions, which really means you have a rolled loop, and that loop has a counter, it's got a scheduled data path, and the tool is generating an FSM under the hood. And as I mentioned before, this is often good enough for simple control flows, for simple or medium complexity feed-forward pipelines. But the problem is implicit FSMs reduce visibility. So you don't know what the FSM is actually doing. So it's harder to predict what the behavior is, what are the exact states it's cycling through. It's more difficult to manage the latency installs or specific pipeline control points. And debugging timing issues can be more complicated. So you need to make a decision when to go explicit or implicit. So implicit FSMs are great for simple or medium complexity, straight line control, but sometimes you want to really explicitly write an FSM like you would in RTL. And sometimes there's a hybrid approach, either combining an implicit FSM with a separate data path, or an explicit FSM where you've actually embedded the data path. So here's an example of an implicit FSM. So this is for coding a DMA controller. This is just actually part of the DMA controller, so I'm not going to spend too much time on it, but I reference it in the next slide. And so this is the power of using high-level SystemVerilog for building designs, is I can do class-based design. And so I've created a generic bus interface class for my DMA controller. This is a parameterized class. I get to specify the data type and the max burst size. It then is encapsulating 3 different channels, so address, data, and control channels. And then it has some tasks that'll allow me to initiate or set up a burst, and then basically, since this is a read bus interface, pop data from the bus interface. So what does it look like coding using implicit FSMs? It's very high level, very simple to understand. So now I've got a DMA reader function. I've got my read master interface. I've got some other channels here because this is going to forward some of this data on to the rest of the design. And then within my DMA reader, I have some control signals. So there's a processor interface that's going to tell this DMA reader when to start. I then call my bus interface class to initiate a burst. I can add in some constraints, so I can force cycles into my pipeline to separate the initiation from the data coming back. And now I have a loop. And the loop is basically going from I equals 0 to I less than burst size. So I've got a programmable burst size coming from my processor control. And then it's basically just going to loop until it reaches the burst size. And as it's looping, it's popping data off, and it's forwarding the data to the rest of the design. So it's super powerful. It's not exact, it's throughput accurate, but there could be differences in latency between this high-level simulation in terms of the FSM behavior. But as you can see, I haven't written any FSM. It is being inferred, or it's implied from the design description. So that's great, but also sometimes you may not want to rely on implicit FSM. You may want to be able to pull your FSM states out and debug them. So just like RTL, you can write explicit FSMs where you define each state, either using switch case or if-else statements. You get to decide exactly when things are going to occur, not by the tool. You get cycle level precision. So if you're writing an explicit FSM, and you're constraining the tool to say, run this with an II1 and fit this into a single pipeline stage, you're going to get exactly what's described in the code. And often this is required. And then, as I mentioned, you have better observability and debug and simulation. So you can really see what's going on. You can add probes in, as we'll see, and see exactly the state transitions. So here's that same DMA controller. Actually, sorry, this is the writer. So I did the reader was using implicit. This is a DMA writer. And so this is pretty much looks like RTL for the most part, except that the IO is transaction level. So even though I am writing, kind of at the RTL level, I still don't have to manage the IO. All the IO transactions are basically built into the synthesis process. So it's still higher level than RTL, but still it looks very similar and it really gives me the control I want. So I'm constraining the design to be a single pipeline stage with a throughput of 1. But now within my SystemVerilog, I can define some states using enums. And then I explicitly am going to transition through these different states. And in this case, I don't even need to worry about, say, putting cycles between the initiation of the burst and the data coming back, because that's implied because I'm transitioning from the initiation state then to the burst state and checking my burst counters and going back. And so you can kind of see there's benefits in both styles. So you can also mix control and data path, and this can be very useful, but also there can be some issues here, and this is usually where people can get tripped up in high-level synthesis. So you can have a switch statement where now you're doing these control decisions like we saw before with the explicit FSM, but within one of those FSMs, you might have very heavy computation. You might be doing kind of data path computations in a FSM state, and the rest are just state transitions, which is pure control. And as we'll see, this can be fine because the tool has the ability to synthesize those data path states and still be able to kind of run at maximal throughput, with the exception as long as there's not feedback. So if the computation is feed forward, it can be pipelined across the different FSM states. However, the problem is going to be is if you have state feedback, and that state feedback is dependent upon a heavy computation within one stage. So you might have kind of data path logic that is then being used to determine the next state. That has to finish within the initiation interval. And initiation interval, you can think of it as throughput. So if I have feedback that needs to happen within a clock cycle, I'm saying my initiation interval is one clock cycle. And so if the feedback to compute the next state is going to take longer than the initiation interval, which ideally we want it to be a throughput of 1, the tool's not going to be able to build it, or it's going to have suboptimal performance. And so this happens all the time, and we'll look at what that means. And then, as we'll see, RISE has the ability to identify that feedback in order to figure out what needs to be done. So here's an example where I'm mixing control and feed-forward data path. I've got a simple two-state state machine. It's got a fetch state and an execute state. Fetch is simply reading an IO and shifting that data through a shift register until it reaches a specific count. And then it goes to the execute state. And then the execute state is basically multiplying all those shift registers together. So this is contrived, but it shows you this is a very heavy state because essentially I've got a multiply tree. And so it does the multiplication. It writes the result of that data path to the output, and then it goes to the next state. And so when you synthesize this, because the next state computation is simple, it's very easy to schedule that within the II equals to 1. And so you can see now what happens here is that the data input is being read in the fetch state every clock cycle. We then reach the execute state, where it's doing the multiply. In this case, it's, I believe, a two-stage pipeline to, or I say it takes 3 pipeline stages. So it's actually, yes, it's 3 stages. The right output is on the 3rd stage to do that multiply tree. And so here's where the multiply computation begins, and the execute state, it does right here, and then it starts over again. So you can see that my light state is running with full throughput, and my heavy state is also able to run with full throughput, even though it's only doing a single write. If I was doing multiple writes, we would see it still running with an II of 1. So
Hey,
this is
Mike?
very useful. Yes.
I'm sorry, we have a quick question here from
Sure.
Venkata. He'd say, would you comment on the case where we have to deal with non-ready valid handshaking scenarios?
When you say non-ready valid handshaking scenarios, what exactly does that mean? You mean no handshake?
Oh, I don't know if I can unmute him for him to clarify that. Let's just see if we want, maybe we take that to Venkata. I'm going to allow you to talk so you can ask a clarifying question. Oops, did I do it?
Well, I can.
Okay.
I guess I can
Okay.
answer. Sorry, were you able to do it?
I will.
Hello.
Yes.
Hi. So, for example, Axie uses this ready valid handshaking signal. So modeling Axie, like how it is done in MATLAB, is pretty much straightforward for HLS. For if we go to APB or SPI, something like that, to model this, how would it be?
I'm not familiar exactly with that protocol, but you're saying that, is it valid only, or
Yeah, something like that. Yeah.
valid only, we haven't. So this is something that's on our to-do list, but for now we tie off the back pressure signal, and basically you just eliminate back pressure. We need to do some work there to basically build a custom IO that is valid only, but essentially you can eliminate the back pressure. You can just ignore the back pressure. But
Okay.
the only thing there, and this is where it debug and is very important, is when you eliminate back pressure, it's up to you to guarantee functionality. And so we're looking at basically embedding in assertions within the RTL to check for these types of things, because without back pressure, if an IO comes and you miss it, then the design's going to misbehave. And that's a modeling issue, because when you model, it's always going to work, right? Because everything happens in a single clock cycle or 0 time. And so if you have latency that's been added to your design, or you're not achieving an II of 1, you could potentially miss a transaction in the generated RTL. And so you have to be able to debug it.
Okay, thank you.
Sure, it's a good question. Okay, so now let me just check my time here. Heavy state feedback is the problem, and it's going to limit the throughput of all states. And this is a classic high-level synthesis problem that I'm going to describe what the issue is, how I would code about it, and at the end I'll talk about some of the work that's being done to kind of automate this kind of process. So when you have a case where state feedback is longer than the initiation interval, it's either going to cause a scheduling, or also, if you've told the tool to just build the design, you're going to get a throughput that's slower than what you were expecting. And this is happening because you're computing the next state, and that computation is taking longer than one clock cycle. And so if you tell the tool to basically achieve maximum throughput, a throughput of 1, and it can't do it, it's going to come back and it's going to say, hey, I can't do this. You need to set a certain throughput. You need to set this throughput and rerun. But now you've got a design that's probably not the throughput that you want. And so I've taken that simple example, and what I've done now is I've taken the output of my data path computation, and I'm using that to decide what the next state is. Again, this is contrived, but it shows the exact issue. And so now, because my next state computation is basically has to go through that multiply tree, it takes longer than a clock cycle, and you're going to get this error from the tool that's going to say, you've set a worst case throughput equal to 1, but the best I can do is 3. So go ahead and rerun it. And this is a manual process. We're looking into automating, kind of doing a 2-pass run to do what I'm going to show. But so you can rerun now with the worst case throughput of 3, and you can do some analysis. And so we have the RISE design analyzer. All this analysis is also, all this information is available in text and JSON formats, so you don't need to run the GUI. I'm a GUI person. I like GUIs because it's also cross-probable, but the text reports also have all the information I'm showing here. So now I've rerun the design with a worst case throughput of 3. Since I couldn't build it. And now I go in and I can do critical path analysis and look at the different pipeline stages. And so I can see here that my critical path in these pipeline stages is basically maxing out based on my clock frequency. I think was 500 megahertz in this case. And so you can click on those critical paths and it's going to take you to that location in the source code. And so now I can say, okay, yeah, so my critical path is a feedback path. It's basically pointing to this section of the code. This is a problem. And if you simulate this, you see now that those light states that we saw before that's loading the shift register that happened every clock cycle are now happening every 3 clock cycles because of this heavy state. And this is unacceptable in most cases, right? You need your FSM, at least say for the light state, to run every clock cycle, because why am I waiting 3 cycles to do a shift operation? So this is a classic problem with high-level synthesis. Often people get tripped up here and they don't know, they can't even identify where is the feedback path. So, we've got these mechanisms to do that, but then what do you do? So currently, probably the most practical thing is to refactor the code for heavy state feedback. And so what this means is being able to identify those heavy states and break those feedback paths in order to allow the other states to run with full throughput. Now, this is maybe less than ideal, and I'll talk about some of the work that's being done. But the reality is you have this heavy computation, and if you can't eliminate it, it needs to take more than multiple clock cycles. So what you want to do is you want to create a separate process for those heavy states. And then within your state machine, you want to basically send the current state data, or whatever the state data or state registers that are needed by that heavy state. You want to create channels to forward that to a separate process. So now I've created a heavy state computation process, and I created a write state where I'm forwarding the required data to that process. And then I go to a read state and I'm reading the state data back. And so now from this FSM's perspective, I've got a simple state transition. I've got an IO, so that can happen in a single clock cycle. I've got here a IO read, which can happen in a single clock cycle, and now a simple state transition. And so I've broken the dependency of the heavy state, and that's now going to allow me to run all my other light states with the maximum throughput. There is a cost here, right? So by creating these internal channels and forwarding the data and wait for it to come back, I'm going to have more registers. There's no avoiding that. You need to basically create registers in order to add this channel communication. And I'm going to add latency, because now, in addition to the latency of the heavy state, it's going to cost me a cycle to send the data, and it's going to cost me a cycle for the data to come back. However, I mean, this is the reality. You're trying to do this type of computation and you're paying this penalty. And so these are tricky problems that often get hidden in high-level synthesis tools, because once it fails, you don't know why it's failing. And so the key here is that you can identify those heavy states, and then you have to basically think about how can I code around it. So when you model and synthesize, you really want to be able to, for control, if it's important, you want to be able to model the cycle accurate behavior. And so having this kind of visibility at the high level is really key. And that means using non-blocking IO and using explicit FSMs where you can where you can really kind of determine or ensure the exact cycle by cycle behavior. In terms of synthesis, if you're not as concerned about the modeling, or the model agreeing with the RTL, if there's some flexibility, or you're only interested in running the RTL, you can also use synthesis directives to lock the latency behavior. So we have the ability either in System C and C++ or SystemVerilog to control the placement of I/O within the pipeline. So I can say this I/O is going to go in pipeline stage 0, this is going to go in pipeline stage 3, and so on and so forth. So we really do have the ability to manage the pipeline latency or the I/O placement in that sense. However, as I'll talk about, that's not necessarily where we want to be eventually. We can see you might have to do a little more work. Manual coding can be, it's more effort, but you can enforce predictable timing. So by using explicit FSMs, you can really define the exact kind of I/O timing. You still have the ability to do things at a high level. You've got transaction level I/O, but you do need to pay attention also, if you're mixing kind of pure control with datapath, as I just covered. And then there's other things you can do in modeling in terms of adding shift registers and buffers to model the delay. But that's I'll talk about that. That's less kind of practical right now. Debugging is important. So anyone that says you don't need to debug your machine-generated RTL is not being truthful. If it's feed-forward simple data paths, you often don't have to debug, right? It just works out of the box, and that's the beauty of HLS. And so we provide a lot of debugging capabilities. You can debug visually, so there's the ability to dump waveforms and look at ready valid signals and enable signals over time. You can track the state transitions if you're putting probes on your FSMs. You can add in synthesizable assertions and displays or print statements to your debug, and this is often required, especially when you start to do these non-blocking I/O type designs. You will find that you've done something and your simulation either at the high level is going to deadlock, or it's going to deadlock when you generate the RTL, and you need to be able to put probes into the RTL to debug this, and we'll look at how that works. You can analyze the channel transactions to identify stalls and bottlenecks. So we gather statistical information on the interconnect channels and the channels at the top level, and that can allow you to immediately identify who's the cause of a performance bottleneck or a stall. And then ultimately, really, right now is you need to adopt the best practices for control-heavy designs. Even though it may be easier to mix the data path and control, as we've seen, then you're relying on implicit FSMs and you have more variability in the generated RTL. So for debugging, bottleneck analysis is very useful and very important. Debugging waveforms is great. You can, if you look at this waveform, you can kind of see, oh yeah, this I/O is not working, and if your design was stalling, you could say, well, because I can see that this data is never being presented to this input, or this output's never accepting the data. But imagine you have 20 channels or 100 channels. It's much harder to visually inspect that and see what's going on. And so what we do is when we run the co-verification using your high-level test bench and the generated RTL, is we are gathering statistics within the channels, and those statistics indicate things such as the number of transactions that happened on that channel, the number of cycles that the design was running for. It'll give you average throughput. So in this case, I've got an average throughput of 1.3 for my data in 0 channel, and you can see the reason why that is it runs for 13 cycles, and 3 of those cycles it's being stalled. You can see on my data in 1, I have 0 transactions for 13 cycles. So there's no activity whatsoever on that. And so you can post-process this transaction information, and it's for more complex designs, it makes it much easier to understand potential causes of either performance bottlenecks or deadlock within a complex interconnect.
Hey, Mike.
Yeah, if you're told you don't need to debug machine-generated RTL, it's not true. You do, although not a lot, but sometimes it happens. And you want to be able also to debug simulation. And so we have the ability for all the languages to basically add probes into the high-level description that will be synthesized into the RTL. So here is one of those simple examples we covered before, where now I'm saying, if I enter the condition that this IO is being read, then go ahead and display the data that came back from the IO. And we are then going to synthesize that display, or it could be an assertion, into the generated RTL. It's guarded, so it's only there for simulation. It has no effect on synthesis. And this allows me then to kind of spread breadcrumbs throughout my design in order to do debug to figure out when things are either deadlocking or there's performance issues. For what's next, I think some of the things we're looking at, but it is definitely challenging, is being able to model latency. So our modeling style is throughput accurate, and it's been that way since MatchLib kind of started doing their things. But being able to model latency is a much more challenging problem, and these are things we're looking at. And it really requires being able to annotate timing on the untimed models, so kind of at the transaction level, in order to get precise agreement between the high-level model and the synthesized RTL, assuming that you're not writing cycle level, explicit FSMs. And then the other thing that I was hoping to show today, but it wasn't quite ready for prime time, is dynamic state feedback optimization, which is being able to automate the kind of code rewrite that I showed for the FSM design for different types of problems where you may have conditional latency depending on which condition branch you execute within a data path. And one might be a heavy latency state and the other one might be a light latency state. And there's already infrastructure that's been implemented in the back end to basically automate those transformations, but I'd say it's probably alpha at best. And so, hopefully within the next couple months, we'll do another webinar. We'll be able to show you some of these advanced optimizations. And I think with that, we can just open it up to questions. Ellie, I'll just leave the summary slide up here, since I think it's somewhat obvious what we talked about, but why don't we just take questions?
I want to thank everybody for coming, and please email us if you have any further questions. And thank you for coming.
Yes.
All right.
Thank you, everyone.
Thank you.